Scientists say 3 newly discovered planets rotating the same star have the potential to sustain life. New Horizons has shown us vistas of Pluto that we have just never seen before. Unprecedented images, including this one. At the far edge of our solar system drifts Pluto, a frozen world once hailed as the 9th planet and later stripped of its title. For decades, it was little more than a faint point of light, mysterious and distant, until the New Horizons spacecraft swept past in 2015 and revealed mountains of ice, flowing glaciers, and a sky wrapped in a striking blue haze. Yet, that flyby was only the beginning. With the James Webb Space Telescope now turning its eyes outward, astronomers are learning that Pluto's atmosphere is stranger than they imagined. Scientists are unsettled, realizing this small body holds clues that challenge planetary models. Pluto demands we watch closer, for it may change how we understand worlds beyond Earth. Pluto's comeback story, discovery, demotion, and the New Horizons surprise. Pluto has always been a world wrapped in intrigue. Long before spacecraft sent back pictures of its icy mountains and shimmering haze, it was only a faint speck of light on photographic plates. In 1930, a young astronomer named Clyde Tombaugh at Lell Observatory in Arizona carefully examined the night sky through painstaking comparisons of images. What he uncovered was an object moving against the background stars. This discovery immediately captured the public imagination. Pluto was hailed as the long-sought 9th planet of the solar system, orbiting in the mysterious regions beyond Neptune. It seemed to fit perfectly into the planetary family, even though its size and brightness suggested it was far smaller than its neighbors. For decades, Pluto's status as a planet was never seriously questioned. It appeared in schoolbooks alongside Earth, Jupiter, and Mars. Children memorized its name as the tiny cold member at the edge of the planetary order. Yet, behind the scenes, astronomers were puzzled. Pluto's orbit was unusually elongated and tilted compared to the 8 other planets. Its small size, barely 2/3 the diameter of Earth's moon, raised questions about whether it truly belonged in the same category. Still, sentiment and tradition held strong, and Pluto remained a planet in the eyes of both scientists and the public. The debate grew louder as the 20th century drew to a close. New telescopes revealed that Pluto was not alone in its distant neighborhood. Astronomers began finding dozens of icy bodies orbiting far beyond Neptune. Many were similar in size to Pluto, and some were nearly as large. The discovery of Eris in 2005, a body slightly bigger than Pluto, forced astronomers to make a decision. Either the definition of a planet would have to expand to include this growing population of outer solar system objects, or Pluto's status would have to change. In 2006, the International Astronomical Union introduced a new definition. A planet must orbit the Sun, be large enough to be nearly round, and, most importantly, clear its orbital neighborhood of other debris. Pluto satisfied the first 2 requirements, but failed the third. With that ruling, Pluto was reclassified as a dwarf planet, sparking outrage and sadness around the world. Many felt that something beloved had been unfairly taken away. While the debate continued, something remarkable was unfolding. NASA's New Horizons spacecraft, launched in 2006, was racing toward Pluto. After nearly a decade of travel, it reached its target in July 2015 and provided humanity with its first close look at the dwarf planet. What New Horizons found was breathtaking. Instead of a dull frozen sphere, Pluto revealed itself as a dynamic world. Its surface was decorated with towering ice mountains as high as the Rockies and vast glaciers of nitrogen ice flowing across plains the size of Texas. Evidence suggested that Pluto might even experience cryovolcanism, where icy materials erupt from the interior rather than molten rock. Perhaps the most surprising discovery was its atmosphere. Against all expectations, Pluto's sky glowed with a bluish hue wrapped in multiple layers of haze, stretching hundreds of kilometers above the surface. This haze was not a simple blanket, but a delicately stratified veil of fine particles created when sunlight interacts with methane and nitrogen gases. The layers scattered sunlight in a way that painted the sky blue. reminding scientists and the public of Earth's skies, yet born from entirely different chemistry. This discovery captivated the world, suggesting that Pluto, far from being a static relic, was active and evolving. New Horizons transformed the image of Pluto from a minor icy body into a fascinating frontier of planetary science. The spacecraft showed that even small worlds at the edge of the solar system can be complex and alive with activity. Despite losing its official status as a planet, Pluto gained something more valuable: scientific respect. Astronomers realized that if such a distant and diminutive object could harbor glaciers, mountains, and an active atmosphere, then many other icy objects could harbor glaciers, mountains, and an active atmosphere. Beyond Neptune might also hold secrets waiting to be revealed. The story of Pluto is therefore not one of loss, but of rediscovery. From its humble beginnings as a speck on a photographic plate to its demotion in 2006, Pluto seemed destined for the margins of science. Yet with New Horizons, it reached the spotlight, commanding attention with landscapes and skies that defied expectations. Its blue haze, its flowing ices, and its complex surface revealed that classification alone cannot capture the wonder of a world. Pluto, though a dwarf by definition, proved itself to be a giant in terms of scientific importance. This comeback story set the stage for what would follow. With the James Webb Space Telescope poised to continue the investigation, scientists were eager to learn whether Pluto's strange haze was merely a visual curiosity or a window into deeper climate mysteries. The answer, as it turned out, would be more startling than they ever imagined. The assumptions scientists carried into the James Webb observations. After the dazzling revelations from New Horizons, Pluto was no longer a blank space on the map. Scientists had photographs, compositional data, and atmospheric profiles, but they still lacked a complete understanding of how this distant world functioned. Much of what was known remained built upon assumptions and models. And while these provided important guidance, they left many open questions that only new observations could answer. When the James Webb Space Telescope prepared to study Pluto, astronomers carried with them a set of expectations shaped by earlier findings. The first assumption centered on Pluto's atmosphere. It was already established that the haze discovered by New Horizons was made of small particles formed high above the surface when sunlight broke down molecules of methane and nitrogen. These fragments recombined into more complex hydrocarbons and nitriles, which in turn clumped into fine grains. These grains were so tiny that they scattered blue light, effectively giving the haze its remarkable color. Scientists believed this process was straightforward and similar in principle to what happens on Titan, Saturn's largest moon. The prevailing expectation was that Pluto's haze was simply a byproduct of sunlight acting on gas, a delicate veil with little influence on the deeper mechanics of climate. A second assumption followed directly from the first. In most planetary atmospheres, gases themselves dominate the movement of heat. On Earth, molecules of carbon dioxide, water vapor, and methane absorb and release energy in ways that regulate temperatures. On Pluto, scientists assumed the same rule applied, although in a far colder and thinner environment. The haze was beautiful, but it was thought to be secondary, floating high above the main processes of radiative balance. The idea that haze, particles themselves, could dominate the thermal structure seemed unlikely. Another expectation concerned the layering of the haze. New Horizons had revealed multiple discrete sheets of haze rising high into the atmosphere. These layers appeared separated by tens of kilom and hinted at complex processes shaping how particles were distributed. Some researchers speculated that waves in the atmosphere driven by winds or surface topography might create the stacked effect, yet the exact mechanism remained mysterious. Before Webb's observations, it was assumed that these layers would remain an unexplained oddity, something to be clarified only by a future mission that could linger longer in Pluto's skies. There was also an assumption about the stability of Pluto's climate. Because the dwarf planet orbits so far from the Sun, it receives only a faint trickle of solar energy. Its atmosphere is tenuous, composed mostly of nitrogen, with traces of methane and carbon monoxide. Many researchers expected that such a fragile system would be relatively simple and stable. Seasonal changes might cause ices to sublimate and refreeze as Pluto moves along its long elliptical orbit. But the overall behavior of its atmosphere was thought to be quiet. Few anticipated that anything unusual or dynamic was happening on scales beyond surface frosts and occasional winds. Finally, there was a belief about the limits of observation. From Earth, Pluto is a tiny point of light, barely distinguishable from a star. Even with the best ground-based telescopes, astronomers could only infer broad atmospheric properties through stellar occultations. When Pluto passed in front of distant stars and caused a brief dimming, New Horizons gave a brief but spectacular snapshot. Yet, it was a flyby, not an extended mission. When the James Webb Space Telescope launched, astronomers planned their campaign to catch Pluto in the right orientation, allowing the telescope to collect hours of uninterrupted data. The resulting spectra were then compared with models built after the New Horizons flyby, which predicted how gases and particles should behave in Pluto's atmosphere. What Webb provided was not just a confirmation of known molecules, but a window into the energy balance of the atmosphere itself. By examining how much heat was emitted at different infrared wavelengths, scientists could determine whether gases or particles were driving the temperature structure. The data showed that haze particles were emitting strongly, cooling the atmosphere in a way unlike any other planetary body yet studied. The process of interpreting these signals was painstaking. Infrared spectra are filled with overlapping features, each corresponding to different molecules. Researchers used computer models to separate these contributions and test how haze particles of different sizes and compositions would interact with light. Only when the models that included active haze cooling matched the Webb data did the surprising conclusion become clear. Webb's observations revealed that Pluto's haze is not a decorative veil, but a powerful regulator of climate. This finding overturned the assumption that gases alone shaped the energy flow. It also explained why previous models struggled to reproduce. Pluto's temperatures, without including haze cooling dot simulations, predicted an atmosphere that was too warm compared to what was measured. For scientists, this was a triumph of technology and perseverance. A telescope built to peer at the first galaxies had also illuminated the hidden workings of a tiny world at the edge of our solar system. Webb proved that even dwarf planets could yield secrets capable of reshaping planetary science. And it confirmed something more profound, that the universe, whether near or far, continues to surprise us when we have the tools to look closely enough. The way Webb studied Pluto is a reminder that discovery is not only about what we see, but also about how we see. By capturing light invisible to human eyes, by separating faint signals from a background of noise, and by testing models against data, astronomers transformed Pluto from a puzzle into a new paradigm. The world once dismissed as insignificant had again forced scientists to rewrite their understanding. And it all began with a telescope watching quietly from 1,000,000 miles away, patient enough to record the faint heat of a frozen world. What this means for planetary science and for us. The discovery that Pluto's haze cools its atmosphere was more than a revelation about one distant world. It opened an entirely new chapter in planetary science. For decades, researchers had assumed that gases were the main actors shaping the climates of planets and moons. On Earth, greenhouse gases trap heat, warming the planet. On Mars, the thin carbon dioxide atmosphere allows heat to escape easily, leaving it cold. On Venus, a dense layer of carbon dioxide and clouds produces scorching temperatures. But Pluto revealed that something else could dominate, something far less expected. Haze particles, though incredibly small, wield enormous power over Pluto's climate. Instead of merely blocking sunlight from reaching the surface, they act as an active cooling system high in the sky. These tiny particles absorb and scatter solar energy, then radiate much of it back into space before it ever warms the ground. The effect is so efficient that it cancels out the heating normally expected from atmospheric gases, leaving Pluto's atmosphere far colder than predicted. This discovery challenges long-standing assumptions about how planetary atmospheres work. It reveals that hazes are not passive byproducts of chemistry, but active regulators of climate. For scientists, this finding is transformative. It suggests that other worlds wrapped in haze, like Titan or certain exoplanets, may be governed by processes far more ubiquitous than once believed. What Pluto shows is that even the smallest elements can redefine our understanding of entire planetary systems. Titan, Saturn's largest moon, is an immediate comparison. Titan also has a thick atmosphere rich in nitrogen and methane, producing a dense haze that wraps the world in a golden glow. Until now, most models of Titan's climate focused on the effects of methane cycles, clouds, and seasonal shifts. But Webb's findings on Pluto suggest that Titan's haze could also be regulating temperatures in ways not fully understood. This changes how scientists will interpret observations of Titan and other hazy bodies in the solar system. Beyond our neighborhood, the discovery matters for exoplanets. Many exoplanets detected so far are far away with atmospheres only studied through faint starlight filtering as they transit their stars. When astronomers see unexplained temperature patterns, hazes may be the missing factor. What happened with Pluto reminds researchers not to assume that gases tell the whole story. Invisible particles could be shaping climates light years away, making some planets more habitable or less stable than expected. For Earth, Pluto's haze provides a valuable lesson. Our own planet has aerosols, tiny particles suspended in the air from natural and human sources. Volcanic eruptions release particles that reflect sunlight and cool the atmosphere. Temporarily, human activity adds aerosols as well, sometimes masking the warming effect of greenhouse gases. Studying Pluto gives scientists a kind of laboratory where the haze dominates completely. Showing what happens when particles become the key driver of climate, this perspective helps refine models of Earth's atmosphere, especially when predicting long-term changes. The broader meaning extends even further. Discoveries like this remind us of the power of curiosity and persistence. Pluto was once considered too small and too distant to matter. It was reclassified as a dwarf planet, leading many to dismiss it as insignificant. Yet each time we return to it, Pluto forces us to rethink basic assumptions. The New Horizons flyby revealed a dynamic surface with mountains, glaciers, and possible subsurface oceans. Now, the James Webb Space Telescope has shown that its atmosphere works in a way unlike any other. Pluto has transformed from an afterthought into one of the most important teachers in the solar system. For the public, there is also inspiration in the way this discovery unfolded. It took decades of effort to design and launch Webb. It took years of planning to schedule and analyze Pluto's observations. It required countless hours of modeling, debate, and revision before the truth became clear. This is science at its most human. A combination of patience, persistence, and imagination led to a result no one expected. That story matters because it reflects how knowledge advances. In the end, Pluto's haze tells us more than just how one icy world works. It reminds us that the universe is richer than our first guesses, and that small things can hold great power. Tiny particles high in the atmosphere can cool a planet. A small world at the edge of the solar system can change our understanding of climate everywhere. And a telescope built to look at galaxies billions of light years away can also unlock secrets in our own backyard. This is why the phrase, "watch closer," carries weight here. Every time we sharpen our gaze, whether at distant galaxies or frozen dwarfs, we discover that reality is stranger, deeper, and more beautiful than we imagined. Pluto's haze cooling is one piece of that vast story. A reminder that exploration is not about confirming what we know, but about finding what we never expected. And it leaves us with a larger question. If even Pluto, once overlooked, has this much to teach, what other surprises are still waiting in the dark, waiting for us to notice them at last? Tell us, how did you feel when Pluto was demoted? Share your thoughts in the comments below. Thank you for watching. See you in the next.